Hello friends. Now in this session we are going to discuss correlation of random process. As the random process is unpredictable, but the observed sample may be correlated at two different times, say t1 and t2. So the random process, that is capital X function t at time t1 and t2, is given as capital X function t1 and capital X function t2 respectively, and the combinedly called as ensemble, which are the set of random variables. Now, in order to determine the correlation, we first define covariance of two random variables, that is capital X function t1 and capital X function t2. So the covariance can be obtained using expectation operator of the two random variables, which are x function t1 and x function t2, and described as covariance of xt1, xt2 equals to expectation of product of xt1 minus mu into xt2 minus mu, where mu xt1 and mu xt2 are the mean value corresponding to random variable xt1 and xt2 respectively. Now open the inner bracket, and after rearrangement we get expectation E function xt1 into xt2 minus mu xt2 expectation of xt1 minus mu xt1 expectation of xt2 plus mu xt1 into mu xt2. Since expectation of xt1 equals to mu of xt1 and expectation of xt2 is written as mu xt2, so this makes the two terms at right side cancels, and we get covariance of xt1, xt2 equals to expectation of xt1 into xt2 minus mu xt1 mu xt2. Now in this expression of covariance, the first term in right side defines the autocorrelation of two random process. So the covariance can be obtained using autocorrelation function. Now in the case of complex random variable x function t, the autocorrelation can be written in general form as r function of t comma s equals to expectation of xt into x star s. Here x star is complex conjugate function. Also, if random process xt is stationary with second order or higher order, the autocorrelation function, that is r function t comma s, is equals to r function t minus s. Next, there is an important point regarding stationary random process in second order. Here the second order stationary random process is constant if the mean value is equals to 0. Which means covariance and autocorrelation are just identical. That is, autocorrelation of random process equals to covariance of random process, or covariance of xt1, xt2 equals to expectation of product of xt1 into xt2. Similarly, in many applications there is no requirement of stationary random process of second order, but in that case it is assumed that stationary random process is required to be a wide sense stationary or weakly stationary. So in general, we assume that all random process of our interest are assumed to be a wide sense stationary random process. Now next we discuss the properties of wide sense stationary random process. First property is, for wide sense stationary random process, mean value is always constant, that is independent of time. Secondly, the autocorrelation of such type of random process depends only upon the time difference, that is expectation of xt minus tau, or expectation of xt plus tau is equals to r function of tau, that is for all values of t and tau. After this, we move to the significance of autocorrelation function, that is denoted by capital R function tau. Basically, autocorrelation describes the interdependency of two random variables. So let us consider a random process x function t at initial time t. Now after delay time of tau second, the random process is given as capital X function t minus tau. So the random process x function t changes to random process x function t minus tau, and the interdependence between these two random processes is given by autocorrelation function. When this change or fluctuation between random process xt and xt minus tau is very fast, then the autocorrelation function, which is maximum at origin, decreases rapidly with respect to tau. So we get an undershoot and overshoot. But when the fluctuations of random process is very slow, then the autocorrelation function decreases slowly from maximum value of our function tau, that is at origin. So it concluded that when the random process xt changes rapidly with respect to time, then at the same rate autocorrelation function decreases from maximum value at tau equals to 0. This decrease in autocorrelation function is characterized by a time called decorrelation time and denoted by tau suffix d or tau suffix naught. Here the decorrelation time is greater than delay time tau. Also, as we know that in practice all the random processes are considered as a wide sense stationary random process with zero mean. So on the magnitude curve of autocorrelation function, decorrelation time tau suffix d is defined as a decrease in magnitude of autocorrelation function by 1% of its maximum value. Here 1% of magnitude is a assumed value. Next we discuss the properties of autocorrelation function, that is capital R function of tau. As we know that autocorrelation function represents the interdependence of random process xt which is observed at time tau second apart. So the autocorrelation function is determined using expectation of the product of xt and xt minus tau, or expectation of xt into xt plus tau for all values of t and tau. So the first property is the maximum value of autocorrelation function is equals to Rx function 0, that is at origin, and it can be obtained using expectation of x square t, and this represents mean square value. So at this point of time, average power of random process xt is obtained as expectation of x square t minus tau or expectation of x square t plus tau. Now second property is autocorrelation function is the even function of tau or called as even symmetry, and the condition is Rx tau equals to Rx of minus tau. And the third property is the maximum value of autocorrelation function, that is Rx tau, is equals to the mean square value of Rx0, that is at origin, and from here we conclude an important point, that is mean square value Rx0 must be greater or equals to magnitude of Rx tau. This can be understood using non-negative quantity of autocorrelation function. So here non-negative quantity of random process xt is expressed as expectation of xt plus minus xt minus tau whole bracket square. That must be greater or equals to 0, which means it is non-negative quantity, and here tau is not equals to 0. After this we expand this equality using formula of a plus b whole square. So it becomes expectation of x square t plus expectation of x square t minus tau plus minus twice of expectation of xt minus tau, and this value is greater or equals to 0. Here first and second term is the property of autocorrelation function, and it is equals to the mean square value Rx0. And the third term is the formula of autocorrelation function, that is Rx tau. So twice of Rx0 plus minus twice of Rx tau is greater or equals to 0, or we can say that Rx0 is greater or equals to minus plus Rx tau. Now in terms of magnitude, we can say that mean square value Rx0 is greater or equals to magnitude of autocorrelation function.